Welcome to our next online lecture. Today we're going to be actually finishing up relativity. So let's have a couple review questions just to begin with. Number one, suppose Usain Bolt carries his own stopwatch. Assuming both his stopwatch and the stopwatch of officials are exactly correct, how do the times compare for Usain to run 100 meters? And assume that he has a constant speed of 10.44 meters per second. That's his average speed for his world record race, just for the record. So the question is, how do the times compare? Are they the same or are they fundamentally different? Before you answer, let's remember this speed here is much, much less than the speed of light. So in reality, they are virtually identical. But relativity says they're not exactly identical. I went ahead and did the calculations here, and it turns out that the difference in time between the two would be would be 5.8 times 10 to the minus 15 seconds. So it's not a big difference, but there is a difference according to relativity, because if you have a moving clock, the moving clock runs slow. Or to put it another way, the proper time is the time in the reference frame where the clock is stationary. So we have two reference frames here. We have Usain's reference frame, where he sees himself as stationary and the ground is flying by at 10.44 meters per second. Or we have the official's reference frame, who sees himself as stationary and Usain is moving at 10.44 meters per second. Now, the official sees that Usain's clock is moving, right? And his own is stationary. Usain sees that his clock is stationary and the official's is moving. So the question is, which one is going to be measuring the proper time, which is always going to be the shortest time possible for the race? Everybody else is going to say it took longer. And the answer is Usain's clock is stationary and it's at the start and the end of the race. So Usain's clock is going to be measuring the proper time, and the proper time is always the shortest possible time. So Usain is going to say, no, I went a little bit faster than that 9.58 seconds that you said it took me. But the other side of that equation is length contraction. Usain would also say, but this race was just a little bit short. In fact, Usain would say that it was about 6.1 times 10 to the minus 14 meters shorter than 100 meters. And of course, we all recognize no one would differentiate those anyway. Second, I think we already had this problem, but just to make sure we understand the proper length, an astronaut leaves Earth in a spacecraft moving at 0.80 c, that's 0.8 times the speed of light, and travels to a star 30 light years away as measured from Earth. It's always important to get those reference frames for measurements. Who measures the proper distance for this trip? So now we have these two objects, the Earth and wherever he's traveling or she's traveling. And a person on Earth sees the starting and ending points as stationary and measures this as 30.0 light years. Whereas the person in the spacecraft is traveling between the two. And so they see that the Earth and this destination are moving. And because they see the Earth and its destination moving, they see this yellow line, if you will, is moving, and thus it's going to be length contracted. So the proper one is the one that sees that yellow line is stationary, and that's the observer on Earth. It's really important to be able to identify the proper frame for distance and the proper frame for time. So that's why I went through these two problems so we could determine the proper time is measured by Usain. But the Earth measures the proper distance or proper length. Now, something we're not going to do any calculation here in the lecture with is the Doppler shift. The Doppler shift is seen all the time. If you have an ambulance coming toward you and it passes you, you hear that the siren shifts from a higher frequency to a lower frequency as it passes you. That frequency shift is what we call the Doppler shift. And for sound, because a sound wave is traveling with a speed relative to the air, has this relationship that the Doppler shift, the frequency that is observed, is the frequency of the source multiplied by the speed of sound in air plus the speed of the observer divided by the speed of sound in air plus the speed of the source. And the conventions for these are V obs is positive if observer is approaching, let's say, approaching source, and V source is positive if I got to get this straight now. If the no, I got one of those wrong. I didn't think about my sign conventions when I wrote this, and so I just have to go through and think it through. So here's the way it works. If the source is moving toward the observer, then it's going to be a higher. So V source is positive if moving away. The observer is positive if moving toward. So there's the sign convention. I didn't think it through when I wrote the equation. Now, if we change from sound waves to light waves, we have a different relativistic Doppler shift equation. And this is specifically the Doppler shift for parallel motion. That is, if something is moving toward or away from the observer. Notice this equation has nothing about V source. That's because we had that principle of relativity that said that any inertial reference frame is equivalent. So V source effectively is always going to be, V source, I meant V observer. Wow. Nothing about V observer because the observer is stationary in his reference frame or her reference frame. So that doesn't appear here because it'd just be zero. But we have C plus the speed of the object divided by C minus the speed of the object. If the object is moving toward us, then it's going to be shifted to a higher frequency. So the object is positive if approaching. Now notice this is only for motion that is parallel, that is coming toward us or going away from us. There is a relativistic Doppler shift if something is going around you in a circle, not approaching or getting farther away. And that's because of time dilation. The time between pulses for the moving reference frame is not the same as the time between pulses for stationary. With the Doppler shift, if something's going around in a circle, there is no Doppler shift because It has to be either approaching or moving away for the sound wave. So we might have an equation doing this in homework, but I'm not going to do any problems with it. It's a very straightforward equation as long as you have your time convention here. The object is positive if it's approaching you. The object is negative if it's moving away. The object is what I called before the source. Now, another thing with relativity is momentum. Momentum, what we learned from momentum was momentum is equal to mv. That was classical physics. For relativistic physics, it's not mv. Momentum has a different equation. It's gamma times mv. Now I want you to notice that there is a shift in symbol here. U is the particle speed relative to the reference frame. So that's U is just when we're talking about the speed of a particle, we use U. When we talk about the speed of a reference frame, we usually use V when we get to this point, relativity. And so gamma is, once again, you replace the V with the U there. So the important thing here is momentum is not just mass times velocity. If you increase your velocity, gamma increases, gets bigger than 1, and so momentum increases at a greater rate than the velocity. And the closer you get to the speed of light, the greater momentum is going to change. So that if you got to the speed of light, remember, gamma as u approaches c is equal to 1 over square root of 1 minus, it's approaching 1, which means that that's approaching infinity. So as you approach the speed of light, the momentum approaches infinity, not mass times the speed of light. Is that important? Absolutely, it's important. First, Newton's second law. I told you, we learned initially that sum of the forces is ma. It turns out that is not correct in relativity. That was an approximation made for, and what I said before, it's approximately correct if the mass doesn't change. Well, when we get to relativity, this here, the second form we learned of Newton's second law, that is correct. This is the correct form, always the correct form of Newton's second law. And so that still applies. Now, of course, for algebra-based students, you just look there, don't need to go further. It's only for David that we have this part. So net force is equal to change in momentum over change in time. Well, remember, that's going to be equals change in gamma mass times particle velocity over change in time. So gamma depends on particle velocity, and so does u. And so that would be a full way of writing it. Something to note here is because the change in momentum is net force multiplied by change in time, if you have a very large force, you will have a quick increase in momentum, but you have to go to infinite momentum to reach the speed of light. So you'd have to have an infinite force or an infinite time to ever reach the speed of light, because momentum's approaching infinity as you approach the speed of light. So that gives you a good argument to say nothing can actually reach the speed of light, because you would either have to have an infinite force or an infinite time to reach the speed of light. Now let's do some problems. Problems are good for the soul. So cosmic rays collide with atoms or molecules in the upper atmosphere. So if a proton has a mass of, and we're just going to put one atomic mass unit. We're just going to use 1 sig fig there. Okay, let's say 1.0 atomic mass unit. And it's moving at 0.70 C. So I have V of the proton initial is equal to 0.70 C. And it has a head-on collision with a nitrogen atom. So nitrogen atom has mass of nitrogen is equal to 14 U. It's initially at rest, so the speed of the nitrogen initial is 0. And then the proton recoils at 0.63 C. Now, note it recoils. So the speed of the proton final is minus 0.63 C. Minus because of the recoil. It's going back, same direction it came from. So the opposite direction. And now the question is, what's the speed of the nitrogen after the collision? Well, if we were doing this non-relativistically, this would be really simple. Non-relativistically, I'll put parenthesis wrong solution would have been momentum initial equals momentum final. So mass of the nitrogen times the speed of the nitrogen initial plus mass of the proton plus the speed of the proton initial equals mass of the nitrogen, speed of the nitrogen final, plus mass of the proton, speed of the proton final. Trying to solve for this, so just rearrange to the nitrogen final equals mass nitrogen v nitrogen initial plus mass proton v proton initial minus v proton final. All over the mass of the nitrogen. You put in your numbers. It's equal to 14 atomic mass units. That's a U. Looks too much like an N for me. Times 0 plus the mass of the proton, 1 atomic mass unit, well, 1.0. Times the initial, which was 0.70 C, minus the final, which is minus 0.63 C, all over the mass of nitrogen, all over 14 atomic mass units. And if you put that in your calculator, which of course I didn't do this beforehand because I didn't think about doing it the classical way, that would be equal to 0.7 minus a negative, so plus 0.63 divided by 14, and that would have given me equals 0.095 C. That's what I would have had for a non-relativistic calculation, but that's wrong. That's just not right. Now, since I did this, which I didn't plan on, I need to add a page. So let's do it the right way then. There's not a lot of point in doing things the wrong way except for to show us the difference in the two approaches. So doing it the right way, I am going to have the same starting point. Momentum initial equals momentum final, because relativity, we still have all of our laws of physics work the same. So as long as we use the right equation for momentum, it's going to be correct. So that's going to be mass of the nitrogen, speed of the nitrogen initial, and then I need gamma for nitrogen initial, plus mass of the proton, speed of the proton initial, gamma proton initial equals, and I'm going to start writing this in the right order, so I have this equation. It's pretty similar. We just have the gammas in there. So first of all, let's just calculate what, wait, not that. Let's rearrange this so we have the thing that 0 will take out. So this is 0. And then I'm going to put the proton on one side and the nitrogen on the other. So I'll have gamma proton initial, V proton initial, minus gamma proton final, V proton final, all times the mass of a proton is equal to gamma nitrogen final, mass nitrogen, V nitrogen final. So if I want to find the speed of the nitrogen final, I'm going to have to calculate these things. And I always do those separately and put the numbers in separately. And then I'm going to have to take these and combine them. So let's just get numbers on the left-hand side. I know I almost always do these symbolically, but here I'm actually going to do numbers. So gamma for the proton initial is equal to 1 over square root of 1 minus 0.70 C over C squared. Notice the C's are going to cancel here. And so it turns out that that is just going to be 1.40028. If I do the same thing for gamma for the proton final, 1 over the square root of 1 minus 0.63 C over C. Again, those C's cancel, and that's equal to 1.2877. Well, let's keep the same number of digits I did before, 2867. And so if I put these numbers in, I have for the whole left side, 1.40028 times 1 atomic mass unit. Well, I factored that out. Times 0.70 C minus 1.28767 times minus 0.63 C. And that was all times 1.0 U. And so that gives me the left-hand side is minus, actually plus 1.7914 atomic mass units times C. Now, you might be a little concerned. I have mass, atomic mass units, speed in units of C. I just have to be consistent with my units. And in the end, I might have to do some conversions, but I'm going to just be consistent until I get to the end. Now, what do I do from here? If I take that, I have it's equal to gamma n final mass n times Vn final. Let's divide both sides by Mn. So I have 1.7914 atomic mass units times C divided by mass of the nitrogen, which is 14 atomic mass units. That's equal to gamma n final times Vn final, which is Vn final over the square root of 1 minus Vn final squared over C squared. So what's the quickest way to solve this? Well, first, let's just divide this out. So once again, I didn't actually do it this way my first time through because I didn't feel like it. That divided by 14. So that's 0.12796 C is equal to Vn final over quickest thing to do, square everything. So I square this and I square this, and I have 0.12796 C quantity squared is equal to Vn final squared over 1 minus Vn final squared over C squared. And there's two ways to skin this cat. I'm going to do it the most obvious way. 0.12796, or whatever that is, yeah. If you square that, that's just equal to 0.016374. So I have that equation. Let us now bring the two Vn finals together. So I'm going to have to make this 0.0. Let me change color just so you can see what I'm doing. 0.016374 is equal to Vn final squared times 1 plus 0.0 16374 C squared over C squared. Notice the C squared over C squared cancel. And so finally, Vn final is equal to the square root of 0.016374 C squared over 1 plus 0.016374. So now, if I did my work correctly, I'll get the same answer I did the first time. Let's just put this in the old calculator just to make sure. Square root of that crazy number divided by 1 plus that crazy number. And indeed, I get the same number. So Vn final equals 0.1269 C. Now, we only have two significant digits here, so that's actually 0.13 C. So you notice that's the speed of the nitrogen when it bounces, when the proton bounces off. And if we compare that to the non-relativistic, it's faster. You have to, but you get a different answer. You have to do it the right way. Now, just a reminder about what we just studied. Which statement is untrue about relativistic momentum? So we have three statements here. Two of them are correct. First, relativistic momentum is conserved. Check. That's how I just solved that last problem. Our laws of physics have to be the same. Second, relativistic momentum is a vector. Absolutely, it's still a vector. It still has direction. So the third one, relativistic momentum is mv. No. Relativistic momentum, got to throw that gamma in there. Now here I used v instead of u, but it doesn't. As long as we know what we're doing, it's okay. So that factor of gamma is the difference. Notice I put it as a vector equation here. I was doing just magnitude above. Moving to another thing of relativity, talking about energy. So what we talked about, our first lecture on relativity, we talked about time dilation and length contraction. Then we talked about how velocities add. This lecture, we've talked about the Doppler shift, about momentum, and now we're going to talk about energy. So one of the first things that Einstein's very famous for is saying that mass is a form of energy. The mass is a measure of what we call the rest energy. If we have something that's just sitting there like a lump, it has a certain energy because of the mass that it contains. And so we have his very famous equation, E is equal to mc squared. But notice that's an E subscript 0. It's the rest energy. It's how much energy something has just because of the mass that it's made of. So that's a fundamental new thing that we have with relativity. We never saw anything like that before. Just a reminder, we saw electron volts before. When we're doing nuclear physics and particle physics, a very common unit for energy is electron volts. So remember, an electron volt is just the charge of an electron multiplied by 1 volt, which is 1 joule per coulomb. So if I take the charge of an electron and multiply by 1 joule per coulomb, 1 volt, I get 1.602 times 10 to the minus 19 joules is what an electron volt is. So that's just a reminder. But we go further than that. We like to talk about things like momentum. Since momentum, mass times velocity was our old version, gamma is our new version, it has units of kilograms times meters per second, right? That's the SI unit. Well, energy, I'll put kinetic energy here, 1/2 mv squared has units of kilograms times meters per second, meters squared per second squared, or kilograms times meters per second times meters per second. And so we take this and we say, there's a nice relationship between this and this. Those are the same. And so if I just take the unit of energy and divide by speed, it'll have units of momentum. And the speed that's convenient in relativity is the speed of light. So we use electron volts divided by c for a unit of momentum. And likewise, mass, we use, I started writing mass, unit of mass. Electron volts divided by c squared for units of mass. So we're going to use these units actually a lot. When we get to nuclear physics, we're going to be doing this a lot more. This makes it a lot easier for us to do calculations because we have things like E equals mc squared. Well, if E equals mc squared and I have a rest mass, well, let's go the other way around. The electron's rest energy is 511 kiloelectron volts. And since E is mc squared, then that means its rest mass, its mass, is its rest energy over c squared. So that's going to be 511 kiloelectron volts divided by c squared, or simply 511 kiloelectron volts per c squared is my unit for mass. So ultimately, I don't have to think here. If I know that it has a rest energy of 511 kiloelectron volts, then I know it has a mass of 511 kiloelectron volts per c squared. I think you can see how that's useful. That is the last slide of the presentation. How I got there will be forever a mystery. Here we go. So a problem just to get some practice with this. What is the momentum of an electron moving at a speed of 0.80 c in units of kiloelectron volts per c? So relativistic momentum. Do I have to use relativistic momentum? Yes. Anytime the speed is greater than 0.1 times the speed of light, you must use relativity. Where do we get that from? Well, gamma would be 1 over square root of 1 minus 0.1 c over c quantity squared would be equal to, and did I do this calculation beforehand? No, I didn't do this calculation. Gamma would be 1.005 in this case. So it would introduce a 0.5% error. Now that's a relatively small error, by omitting the relativistic if it's 0.1 C. That's why we can go ahead and omit the relativistic calculations if it's less than 0.1 C, because it's a small error. But that's our basic rule of thumb. If it's bigger than 0.1 C, we will use relativistic calculations. So that means momentum is equal to gamma m, and I'm going to use U this time just to be consistent. So what is gamma? So this is, that's for determining if we have to use it. So gamma for this problem, 1 over the square root of 1 minus 0.80 C over C. Quantity squared. We actually did this a lot in the previous lectures. That's 1.66 repeating. And so the momentum is going to be 1.66 repeating times the mass, which is 511 kiloelectron volts per C squared, multiplied by a speed of 0.80 C. Now, if we look at our units, one of these C's cancels with that C, and then I just have to multiply my 1.66 repeating times 511 times 0.8, and that gives me a momentum of 681.3 kiloelectron volts per C. And I have only two sig figs, that's 680 kiloelectron volts per C, putting it to correct significant digits. So simple calculations when we use the shortcut. The shortcut is the units. Another problem for us. Carbon dating is based on the radioactive decay of a carbon-14 nucleus, that is 6 protons and 8 neutrons, into a nitrogen-14 nucleus, that's 7 protons and 7 neutrons. In the process, an electron and a particle called an antineutrino are created. The reaction is written as shown here. So we put up here in the superscript is the number of things in the nucleus. I did not write these because C means that it has 6 protons, N means that it has 7 protons. So that's how those are written. Notice this is a nitrogen plus. It's missing an electron because the carbon had 6 electrons around it, neutral. You didn't take away or add an electron to the cloud, so the nitrogen also has 6 electrons, so it has a +1 charge. Find the energy released by this reaction. Well, how do I find the energy released? I find the energy released by comparing the masses. Here's my parent. Here's my daughter. So the mass of the parent is equal to the mass of carbon-14. The mass of the daughter is equal to the mass of nitrogen-14, but it's missing an electron. But then we have that extra electron. So this here is the mass of the nitrogen-14 that's missing an electron. But then I have the mass of the electron that was emitted, plus the mass of, we call that an antineutrino. Now, the antineutrino's mass is negligibly small. So we will take that mass of the antineutrino and say that's approximately 0. Notice minus mass of electron plus mass of electron, those add out to 0. And so what we do is we just say, okay, what is the difference in mass? Mass of the parent minus the mass of the daughter. And then we use C squared because we have the equation rest energy is equal to mc squared. So we have the rest energy on the parent side minus the rest energy on the daughter side. Energy can't be created or destroyed. It's got to go somewhere. So the energy released is the difference in these. So now I just put in my numbers. So the mass of the carbon-14, 14.0032419888 atomic mass units, minus the mass of the nitrogen-14, 0.74005 atomic mass units. And then I need to multiply that by C squared. And I'm just going to write C squared now. So if you do that calculation, the number in parentheses is I've already done the calculation, so I just look at my numbers. 0.000 zeros 1679835. That's probably more digits, but it's correct digits. Times c squared. Now we do something. This u times c squared occurs all the time. And so we take a relationship, one atomic mass unit is 1.66 times 10 to the minus 27 kilograms. I only put 3 significant digits there. Or 931.48 MeV per c squared, because MeV per c squared is just a unit of mass. And so I'm going to replace that c squared. Well, I'm not going to replace the c squared. I'm going to use my conversion factor of 931.48 MeV per c squared per atomic mass unit. Now, if we look at our units, my atomic mass unit cancels. C squared here and over c squared cancels there. And once again, it's just multiply those numbers together. And when I multiply those numbers together, I get 0.156 mega electron volts, or 156 kiloelectron volts. So that's how much energy is released when you have a carbon-14 decay into a nitrogen-14. Now I'm going to come back to that problem, but I have a few slides in between. There are some things that we say are invariant. That is, they don't change when you go from one reference frame to another. One of those things is the speed of light. The speed of light, that was one of our theorems, or our not theorems, not hypotheses. One of our principles of relativity is that the speed of light in vacuum is always the same. It's invariant. It doesn't change as we move through inertial reference frames. Another one is the mass. And just for a historical note, I mean, I'm not that old, but when I was in college, I actually learned that the mass changed with speed. And now we have come to describing it a different way, saying the mass is constant. It's an invariant. Distances and times, things that we usually think is invariant. We think the distance between Denver, Colorado and Lincoln, Nebraska is a fixed distance. But depending on your reference frame, it could be shorter. Length contraction. We tend to think that the time that it takes for the sun to go around the earth is a constant. But depending on your reference frame, it could be different. Those are not constants. They're not invariant. Excuse me. We've talked about force. We've talked about momentum, Newton's second law. We've talked about energy, the rest energy. But what about kinetic energy? When things are moving, they have kinetic energy. So we've learned that kinetic energy is 1/2 mass times speed squared, right? That was simple enough. Not the case for relativistic kinetic energy. So what do? Well, we start with the work-energy relation. The work-energy relation was that the work net was equal to force dot delta x. Or if you wanted to be more careful and do it correct, you had f dot dx and you integrated. Of course, this isn't a calculus class, so that right-hand side, the integral of force dot dx, is not something that you need to do. But here's the work. So this is just showing the calculus steps. It seems like it's kind of simple, but it's not. We have to replace force with Newton's second law, the derivative of momentum with respect to time. And then we shift the dt over, and we have dx dt is velocity, so dp dot dv. But dp is gamma mv, and it's always the same direction as v. And so we have v times d of gamma mv, which is not simple because gamma is dependent on v. So there is a lot of math in here. I just show it so you can see there is math. You don't have to know this. Or understand it. What you have to know is that we took the work-energy relation And using calculus, we were able to derive an equation that said that kinetic energy is gamma minus 1 times mc squared. Where gamma, of course, is that Lorentz factor we've been using all along. So it's a little more complicated equation for kinetic energy. When you look at this, you might say, wait, kinetic energy doesn't depend on speed? But remember, gamma does depend on speed. So speed is in there. It's just in there in a funny way. And it seems like this is really wrong. But it's not. And in fact, in a couple slides, I'm going to go ahead and show you that this agrees with what we've learned. But right now, I want to break this down. Kinetic energy is gamma minus 1 mc squared, or you can write it as gamma mc squared minus mc squared. Well, mc squared, that was our rest energy E0. So kinetic energy is equal to gamma mc squared minus E0. Well, if I add E0 to both sides, then I must have E0 plus kinetic energy, that is the rest energy plus kinetic energy is gamma mc squared. So it turns out this here is the total energy E. So total energy is gamma mc squared, kinetic energy is gamma minus 1 mc squared, and rest energy is mc squared. So here we have what I just said. Now, the principle of complementarity says that when you have some special realm of physics and you have some new physical equations, in the classical realm, they have to agree. So that means our new kinetic energy equation, that kinetic energy, K is often used for kinetic energy instead of KE, is gamma minus 1 minus mc squared. That needs to agree with the classical equation of kinetic energy is equal to 1/2 mv squared. And it doesn't seem like it does. Notice that as v approaches 0, that's we're in the classical realm, then gamma approaches 1 and kinetic energy approaches 0 because you have 1 minus 1 mc squared. So at least if it's at rest, we know that it's going to be right. But what about other values? So we turn to using a Maclaurin series. So if we take a Maclaurin series, function of x is equal to blah, blah, blah. It gives us what we call the binomial expansion, which says if I have 1 minus x raised to the nth power, that's equal to 1 minus n times x plus n minus 1 times n over 2 x squared plus, and a whole bunch of other terms. So if we take gamma, I can write gamma, remember gamma, Lorentz factor, 1 over square root 1 minus v over c quantity squared. Square root is to the power of 1/2, so that's 1 over 1 minus v over c quantity squared raised to the 1/2. Or if I invert it, just change the sign. And so that's what gamma is. And so that means my x is v over c quantity squared in this equation. So if I just take the first terms, I'm going to have, so n is minus 1/2 because that's the power it's raised to. X is v over c quantity squared. And if I put that in, I'm going to have 1. Okay, the first term is 1, so there's the first term. The second term is n is minus 1/2. And then x is this v over c quantity squared. Notice there's a minus and a minus, so it becomes a plus. So gamma is approximately equal to 1 plus 1/2 V over C squared for V over C is very small. This is only correct if X is small. Now, if I plug that into my kinetic energy equation, gamma minus 1 is going to be, here's my approximation, subtract 1, those subtract out now. And so I have 1/2 V squared over C, well, V over C quantity squared times MC squared, cancel our C squareds, and I have 1/2 MV squared. So perfect. My relativistic kinetic energy matches my classical kinetic energy if I have speeds that are of classical speed. Now we're coming back to that radioactive decay of carbon-14. We calculated that it released 156 kiloelectron volts of energy. If all of that energy is kinetic energy for the electron, how fast is the electron moving? Well, our approach is pretty simple. Kinetic energy is equal to gamma minus 1 mc squared. So if I want to find the speed, fundamentally I have to solve for gamma. So kinetic energy over mc squared is gamma minus 1. Add 1 to both sides. And I have gamma is equal to 1 plus kinetic energy over mc squared. So that's 1 plus the kinetic energy was 156 kiloelectron volts, and the mass is 511 kiloelectron volts per c squared multiplied by c squared. Notice that my c squareds cancel, my kinetic or kiloelectron volts cancel, and I just have 1 plus 156 over 511. Well, you do 1 plus 156 over 511, and you get 1.3053 for gamma. And now I just need to find the speed from that. So since gamma is equal to 1 over the square root of 1 minus v squared over c squared, if I square both sides, I will have gamma squared is equal to 1 over 1 minus v squared over c squared. Just swap and you have 1 minus v squared over c squared equals 1 over gamma squared. Getting close. Now I'm going to move the 1 over here, so I'll subtract 1 from both sides, and then change the sign of everything. So I have v squared over c squared is equal to 1 minus 1 over gamma squared. And finally square root it. And I have v is equal to c square root of 1 minus 1 over gamma squared. And so if we do that calculation, we have 0.643 C. So that electron's whistling out of there, right? 64% the speed of light. That's everyday life when you get to particle physics. Relativity is very important in particle physics because you have this kind of crazy speeds involved. Now here's some equations that may prove useful from time to time. So this first equation, it takes some work to get there, but it's the total energy squared is equal to the rest energy squared plus parenthesis momentum times speed of light quantity squared. Now, since energy is equal to kinetic energy plus rest energy, then if I square that, I'm going to have kinetic energy squared plus rest energy squared plus 2 kinetic energy times rest energy. And so if I compare the equation I just did in purple with the equation below, then I'm going to have that E squared, if I subtract E0 squared from both sides of this, I would have E squared minus E0 squared equals PC quantity squared, which must equal kinetic energy squared plus 2 kinetic energy times E0. So this third equation, or now the third, it was the second printed equation, simply followed from the equation above it and the definition, the total energy is kinetic plus rest. This final one, another very useful thing, momentum multiplied by speed of light over the total energy is equal to speed over c. So you can quickly, if you know the momentum and the energy, you can quickly calculate the speed. I could have saved myself a lot of time in this calculation, couldn't I? Because I had the kinetic energy and I was looking for the speed. And so, well, I'm pretty sure I could have, but yeah, I could have used this equation here. Is that the easiest? Actually, probably this one here is the easiest to calculate the momentum. And then once you have that, you use this equation to calculate the speed. Anyway, I could have done it more easily with these equations. So you don't have to do things the hard way like I did here. You can do it easier using these equations. Now, a quick question. What's the rest mass of a photon? What is a photon, you ask? A photon is a particle of light. So what's the mass of light? If you said 0, you're right. There is no mass to light. It's a massless particle. Now, everything we studied, everything that's going to be on the exam we're having next week, is about the wave nature of light. But Einstein said that light behaves as a particle. And so we're going to come back to this after we finish relativity. So light being a particle, particles have momentum. Light has energy and it carries momentum. So first, this is actually Planck's relationship that Einstein took to heart. The energy of a photon is a constant, Planck's constant, H is equal to 6.626 times 10 to the minus 34 joules times seconds. That's just a constant multiplied by the frequency. So the energy for a particle of light is proportional to the frequency. And of course, light has a speed that's the speed of light. And I kind of duh. What is the speed of light? Well, it's the speed of light. So if I take these two relationships and I put them into the equation above to calculate momentum, momentum will be equal to V times the total energy over c squared. But if I put in my equation for energy, I have that. Now this is written as a vector equation. Let's drop the vector sign and just have momentum is equal to the speed. Well, the magnitude of the speed is c, hf over c squared. So cancel one of those c's, h times the frequency over the speed, or since wavelength times frequency is equal to speed, then frequency over speed is equal to 1 over wavelength. So this is equal to Planck's constant divided by the wavelength is the momentum of light. So light carries momentum. So what's the momentum for a photon from a helium neon laser? Wavelength is 632.8 nanometers. My momentum will be Planck's constant over that wavelength. So that's 6.626 times 10 to the minus 34 joules times seconds divided by 632.8. Nano means 10 to the minus 9 meters. And so if I go ahead and just multiply that through, 6.626 times 10 to the minus 34 divided by 632.8 times 10 to the minus 9, that will give me 1.05 times 10 to the minus 20. I did this calculation beforehand, but I clearly, oh, no, I did it right. Times 10 to the minus 27 kilograms times meters per second. So that's the momentum of a photon from the helium neon laser, which is pretty cool, I think, to be able to calculate that. When I was in college, we had an advanced physics lab, and my classmate Greg Frickman actually did an experiment to measure the momentum of the photons of a helium neon laser. What he did was he had a piece of aluminum foil, and he had it hanging from a torsional string. That is a string that when you twist it, it has a relationship that torque is equal to some constant, so I'll put K here, times the angle that it rotates by. And then he would shine a laser beam of known intensity onto that at a known radius, and from that torque and from the intensity, he was able to calculate how much momentum each photon was carrying. Okay, we're getting right here to the end, the next last slide. An electron has a kinetic energy of 1 mega electron volt. Find the electron speed and its momentum. Okay, this isn't hard. Yay. Why is it not hard? Because we know it's kinetic energy. It's gamma minus 1 mc squared. And we know it's an electron. So electron has mass of an electron is 511 keV per c squared. And so I can, I know the m, I know c squared, that's a constant. I can calculate gamma real quick, just like we did before. Gamma is 1 plus kinetic energy over mc squared. We did that equation before, so I didn't derive it again. Equals 1 plus 1,000 kiloelectron volts over 511 kiloelectron volts per c squared times c squared. Notice I had to have the same unit, so I changed mega electron volts to kiloelectron volts. Well, this is almost 2, so 1 plus almost 2, it better be almost 3, and it comes out to be 2.9569. So now that we know gamma is 2.9569, we can say V is equal to square root of 1 minus 1 over gamma squared equals square root of 1 minus 1 over 2.9569 quantity squared equals, forgot to type C out here. So that's equal to 0.941 C. Okay, so now I did this the same way I did it before, right? The hard way. Let's do this what I would consider the easier way. So how would I do this the easier way? Well, if we look at these relationships right here, we have that it's funny because when I did this before, I did the same thing. The total energy, the rest energy, and momentum. And so I could calculate the momentum, and I'm going to just okay, come on. So we have the total energy squared. Thought I had the red pen. Well, let's go to the blue pen anyway. the total energy squared is equal to the rest energy squared plus PC quantity squared. So PC is equal to the square root of E squared minus E0 squared. And then we have the second relationship was that PC over E was equal to V over C. I think that's right, but I'm going to actually scroll because I don't want to make a mistake here. PC over E is V over C. And so that's substituting from above, square root of E squared minus E0 squared over E is V over C. So that's equal to square root of my total energy is going to be, I had 1 mega electron volt for kinetic plus 0.511 mega electron volts for rest. So it's going to be 1.511 MeV quantity squared minus the 0.511 MeV quantity squared, all divided by 1.511 MeV. So that calculation is a little simpler. And if you do that calculation, it better come out the same. And of course, haven't done that calculation yet because I solved it the same way I did the first time. So equals square root of this plus this squared minus this squared divided by this plus this. And it gives me exactly the same thing, 0.941. Now that's V over C, so V is equal to 0.941 C. So I think you can see the blue work is simpler than the red work, especially because I cut out some of the derivation stuff for the red work to make life easier the second time through. So that's why we like to use these equations to simplify our work. Okay, my last slide. When do we have to use relativistic calculations? We have to use relativistic calculations anytime these are not true. So if your momentum is much less than mc, you don't need relativity. If your kinetic energy is much less than mc squared, don't need relativity. If gamma minus 1 is much less than 1, don't need relativity. If V is much less than C, you don't need relativity. Right, that's the end. Have a great day. I'll see you later.